Hello everyone, my name is Oksana, and today I will talk about hypergraph representation via axis-aligned point-subspace cover. This is joint work with Joachim Sporhauser. I will start with a well-known topic of the research, namely geometric representation of graphs and hypergraphs. There are different types how to represent graphs or hypergraphs. For example, contact representation or intersection representation, or covering representation. We focused exactly on the third type of representation. Here in this example, a set of points are covered by rectangles. Each such instance, or any other instance of covering representation, can be represented as a hypergraph, where points are vertices of the hypergraph and covering objects are hyperedges. Or other way around, where points are hyperedges and covering objects are vertices. We considered one of the problem of covering representation, namely point line cover. In this problem, we are given a set of points on the plane and a set of lines. Every such instance can be represented as hypergraph as follows. The set of lines are the vertices on the plane, and a set of points are hyperedges that contain these vertices. In this example, this yellow vertex lie on these three lines, which are represented by these three vertices in the hypergraph that are inside this yellow hyperedge. Trivially, every point line cover instance can be represented as a general hypergraph. But not every hypergraph can be represented as point line cover instance. In this small example, two hyperedges share these two black vertices. Obviously, the corresponding lines in the point line cover instance can be intersected in at most one point, which would mean that these two hyperedges should correspond to the same point. Out of this arises a trivial question. Is there a simple combinatorial characterization for such hypergraphs? It was asked more than 20 years ago, but none simple combinatorial characterization has been found yet. In our paper, we considered a special case of point line cover problem, where we forces lines to be axis parallel, like here. Every such instance can be represented as usual bipartite graph, where on different sides you have vertices corresponding to lines that are parallel either to x or to y-axis. But in this case, every bipartite graph can be represented as point line cover instance, because the adjacency matrix of every bipartite graph has this grid-like structure. Okay, if the problem is so simple and trivial in 2D, what about higher dimension? Here we have an example of axis-aligned point line cover instance in 3D. Every such instance can be represented by a hypergraph as follows. For example, this vertex corresponds to this hyperedge. This vertex corresponds to this hyperedge. And we can do all vertices in this manner. It is not difficult to see that each hyperedge has exactly three vertices, one from each group. We call such hypergraphs three-uniform and three-partite. If the first property is easy to check, the second one is NP-hard already for three groups. That's why, from now on, we consider only three-uniform and three-partite hypergraphs. Now let's summarize what we have. So every axis-aligned point line cover instance can be represented as k-partite k-uniform hypergraph. But what about other way around? can every K-hypergraph be represented as axis-aligned point-line cover instance? We already have seen the answer that even this small example cannot be represented as axis-aligned point-line cover instance because the intersection property does not hold. The exception is 2D, where all bipartite graphs can be represented. The natural question arises, which K-hypergraphs can be represented by axis-aligned point-line cover instances? In the rest of my talk, I will answer this question. I will start with some definitions, and the first one is a definition of an ST-path. By ST-path, we mean a sequence of vertices such that two neighboring vertices in the sequence belong to the same edge. In this example on the bottom, these four red vertices create a path between S and T, or these four vertices. Now let's move to the main definition of this work, vertex separability. For a given K-hypergraph, two distinct vertices from the same group are separable if there exists some other group such that every path between these two vertices contains a vertex in this group. Informally, you can imagine this as by removing one group of vertices from the vertex set and from the edges, it separates these two vertices. In the example of the bottom, all paths between V and V prime, between these two vertices, goes through the green group. So by removing this group, V separates V and V prime. If every two vertices from the same group are separable, such hypergraph is called vertex separable. This is the main property of this work because it already gives us the characterization of hypergraphs that can be representable via axis-aligned point-line cover instance. The main result of our work. We can show that hypergraph is representable if and only if it is vertex separable. Now I will show you how from a given hypergraph get an axis-aligned point-line cover instance. First, I remind you that hyperedges represent points in the point-line cover instance, and vertices represent lines. For each group Vi, we use usual auxiliary graph Gi that gives us the ice coordinate for the points and for the lines. In this small example on the bottom, we have three groups. That's why we create three usual graphs, G1, G2, and G3. The first graph will give us the first coordinates for all lines and all points, the second correspondingly, the second coordinates, and the third one, the third coordinates. Every hyperedge in the hypergraph becomes a vertex in every auxiliary graph Gi, and two vertices are adjacent if and only if they share a vertex not in Gi, in some other group. For example, in the first graph G1, black and gray vertices are adjacent because the corresponding black and gray hyperedges share green vertex here. Similarly, we can create edges in G2 and G3. Now, we count the connected components in every auxiliary graph Gi. Give them some numbers. For example, G1 has two connected components, the red vertex here and these two vertices, and we give the corresponding vertices numbers 1 and 2. G2 has only one connected component, so all vertices becomes 1, and G3 correspondingly 1 and 2. These numbers are exactly our coordinates for the corresponding points in the point line cover instance. So every point that is corresponding to the hyperedge gets its own coordinates. For example, the red point corresponding to this red hyperedge gets 1, 1, and 1. Now we have to define coordinates for every line that correspond to every vertex in our hypergraph. Notice that each line has one free coordinate and two coordinates should be the same as the corresponding coordinates for points that lie on this line. For example, here we have 3 lines that correspond to 3 points, the orange one, the blue one, and the green one, that cover our red vertex P-E1. It means that they should have coordinates similar to this one, but with one free coordinate that correspond to the axis to which this line is parallel. For example, the line parallel to the first axis has the first coordinate free, which we denote as point. The second and the third coordinates should be the same as the coordinates for the corresponding point. Similarly for the rest. Now the lines that correspond to the vertices on which lie the second point that correspond to this black hyperedge should have the same coordinates as these points, but one coordinate should be free. And similar for the lines that contains the third gray point. These arrows means that the first line has the same coordinates as this one because actually they correspond to the same vertex here. And if it would not hold, it would mean that this hypergraph is not representable. Our small example using these coordinates that we defined will look like this one. We explained how from a given hypergraph get a point line cover instance. We can use this to create an algorithm that would check if the point line cover instance is valid by just checking if two different hyperedges corresponded to two different points and two different vertices in our hypergraph correspond to two different lines in the point line cover instance. If it does hold, we get our point line cover representation. Now let's prove that if there exists a representation, then the corresponding hypergraph is vertex separable. We show this by contradiction. Assume that a hypergraph is not vertex separable, but it has a point line cover representation. Then it would mean that this graph contains at least two distinct vertices from the same group that are not separable. In our example in the bottom, these two blue vertices are not separable. Then, for each group, except for the one to which our vertices belong, there exists a path such that each vertex in this path does not go through this group. In our example, for the group V1, there exists a path between V and V' that goes only through the third group. In this case, for V3, there exists a path between V and V' that goes only through the first group. It means that all lines that represents the vertices in those pairs lie on the same hyperplane perpendicular to the j's axis. In our case, if we consider these pairs between v and v prime, it means that the lines corresponding to v and v prime should lie on the same hyperplane perpendicular to the first axis. But from these pairs, the lines LV and LV prime corresponding to these two vertices should lie on the hyperplane perpendicular to the third axis. But then lines LV and LV prime should lie in the intersection of these hyperplanes, the red one and the black one. But the intersection is only one line, which gives us that LV and LV prime should be the same, which contradicts our assumption that they are distinct. In such way, we showed that if there exists a point line cover representation, then the hypergraph is vertex separable. Now, going to the further results, we were able to generalize our vertex separability property to L-dimensional subspaces. What I mean with this? So, in my talk, I talked about lines as covering objects in d-dimensional space, and we showed that all vertex separable hypergraphs have such representation. We also are able to give the polynomial recognition algorithm out of the proof of the main theorem. If we consider d-1 dimensional subspaces as covering objects, then all hypergraphs are representable. This is somehow similar to the representation of bipartite graphs in 2D. But what is in between? If we consider general L-dimensional subspaces between lines and d-1 dimensional subspaces, we could generalize our vertex separability property in this case. The only problem is that the algorithm out of this property is polynomial but for a fixed d. So the first question would be, what about non-constant d? The other open question is, what can we do with these vertex separable hypergraphs? Can we use them to design improved algorithm for problems like vertex cover or matching? What about relation to other graph classes? Thank you for your attention and for possibility to talk to such international audience.